In 1986, Jim Kajia introduced the rendering equation, pioneering the field of realistic computer graphics. His work has allowed for the development of realism in computer graphics and is being used to further explore how lighting can be replicated. The equation is used to replicate realistic properties of light by simulating its behavior in a virtual environment. It is used in computer-generated graphics, commonly referred to as CGI, allowing for complex, realistic lighting and reflections in computer renders. This is the rendering equation. Although it may look very complicated, it can be broken down into a few major parts. We can start off with the left side of the equation. This part of the equation represents the output of the rendering equation and is known as the total spectral radiance. In other words, it is the light that the observer will see. Within this part of the equation, the variable x represents a location in space, and omega O is the final outgoing direction of light. Now, to calculate what light we will see, we have to look at the light emitted and the light reflected from the scene. Starting with L of E, this function represents the light emitted from point x. Omega O represents the direction of the emitted light. For non-light sources, this value will be 0, and for light sources, it will be a value above 0. Let's cover reflected spectral radiance. As the name suggests, this is the light reflected from a position x with omega O representing the direction of the outgoing light. It can also be broken down into simpler parts. L of I, the incoming light, omega I times the surface normal, the Lambert term, and F of I, the BIDF, which we will cover later. Reflected spectral radiance is given by an integral that goes over the unit hemisphere, represented by the capital omega symbol. In simpler terms, this means we will evaluate the right side of this equation for all incoming directions. Moving on, the following part of the equation is the bidirectional reflectance distribution function, or BIDF. Essentially, this function shows how objects look differently when viewed from different angles. The BIDF can calculate where and how light will scatter when it comes into contact with a certain material, taking into account many variables such as material transmission, reflection, absorption, and others. To further understand this concept, we can take a look at a few examples. Assume that a light source is presented as shown, and that a solid glass panel is laid flat on the ground. We know that due to a mirror's reflective properties, the light will bounce off in one direction only, without a disruption to the light's course. This is described as specular reflectance. On the other hand, we have diffuse reflectance. Assuming the light source is constant, but now the glass panel is replaced with a piece of carpet, light will scatter off the surface in multiple directions due to the uneven structure of the object. Therefore, the reflection is not perfect. Due to this scattering of light, the object may look different when viewed from a different angle. Before understanding the final part of the integral, we need to understand what the normal, or n, represents within the rendering equation. The normal represents a vector that is perpendicular to the tangent of the surface point x at which the light behavior is being determined. For example, if x is a point on the floor of the scene, then the normal would be a perpendicular vector pointing up towards the ceiling. The final part of the rendering equation represents Lambert's term. This is the weakening factor of light depending on the incoming angle. Lambert's cosine law ensures that a diffuse reflection is stronger when the incoming light is closer to the surface normal. The rendering equation is a complex yet useful equation, especially in the field of computer graphics. It is the foundation of analyzing the behavior of light and an essential tool in recreating these properties within a computational environment. This equation brings together complicated maths topics with the captivating realm of computer graphics, allowing for the creation of extremely realistic virtual environments. We have heavily simplified the concepts of this equation in this video, and recommend that you conduct further research into the topic if it interests you. Thank you for taking the time to view our submission.